All right, so let's just do an example of the orthogonality algorithm. So let's suppose we're given a basis of 3 vectors in R4. So those are going to be our 3 vectors. And so these 3 vectors span a 3-dimensional space within 4 dimensions. So it's not going to span everything. It's going to be a hyperplane. And what we want to be able to do is describe the grid of that hyperplane using a square grid as opposed to just a random grid based upon these 3 vectors. So we want to orthogonalize and normalize these vectors so that it works. So what we're going to do is we're going to apply the process we did before. So these are our B vectors. These are the starting vectors. And the goal is to find vectors v1, v2, v3 that span the same thing. Right? They have to be orthogonal and their lengths have to be 1. So we're going to apply the same process as before to achieve this goal. All right, so the first one that we did was we did B1. Well, B1, what we did is we just normalized this. We divided it by the norm, and that gave us V1 right away. Right, so just like before, the very first step we did is this is the first step that we did. We just normalized the first vector. We divided by its norm to get a vector of length 1. So we're going to do that right here. So that means that to get V1, all we're going to do is take 1, 1, 1, 1 and divide it by its norm. And this norm right here on the bottom is just the square root of 1 squared plus 1 squared plus 1 squared plus 1 squared. So that's square root of 4 or 2. So that just means we're going to divide everything by 2 to get V1. So V1 is just 1, 1, 1, 1 divided by 2, or 1/2, 1/2, 1/2, and 1/2. And that's going to be our V1. All right, so that was easy. Now things are going to get slightly more complicated. To find our next vector, we're going to take B2, and we're going to project away the projection of that vector on V1. So just like up here, we're going to project away right here. This is projecting away. And then we're going to normalize it. So project away and then normalize. So we're going to have project away means we're going to subtract off the projection of B2. We'll just write B2 for now. Onto V1. So for the concrete vectors, this is -1, 1, 1, 3 minus the projection of -1, 1, 1, 3 onto V1, which is now 1/2, 1/2, 1/2, and 1/2. So it's just a matter of computing this, and this is going to give us a vector W2. That W2 is then the vector that's orthogonal to V1, but not necessarily normalized to V1. And then we'll just normalize it. So this is kind of the hard part. And so we just need to figure out, okay, what is this projection? Well, this projection is just going to be 1/2, 1/2, 1/2, 1/2. We're going to do that again. We're going to do it one more time. Right, so I write it like this because I just want to emphasize that this is how you can write it linear algebraically. This is actually a matrix. Right, so this is the matrix. And we just multiply this times the vector -1, 1, 1, 3. But we can associate this in any way we want. So we're going to do this association. We're going to group them like this. And this is exactly the arithmetic that you were used to in calculus. But I do want to emphasize that there is a hidden matrix in there that's given to you just by these vectors. One other thing that's really nice is because this is normal and the length is 1, this right here should just be 1, right? This right here is just equal to the norm of v1 squared, but we know that that's 1 squared because that's v dot v, or v transpose v. So we know that this denominator should be 1. If we've done it correctly, we actually don't need to do that. So that denominator is just 1. So what are we left with? On top, we have 4 halves with this dot product right here that gives us 4 halves times the vector 1 half, 1 half, 1 half, 1 half. And so altogether, that gives us a vector that's 1, 1, 1, 1. And so that's what we're going to subtract away, right? The projection is what we're projecting it away. We don't want it anymore. So we're going to then subtract minus 1, 1, 1, 3. And now for W2, we get minus 2, 0, 0, 2. So this is our W2. And now, of course, one issue with this is that is not a vector of length 1. It's much larger than 1. It has an entry larger than 1. So to find our V2, what we're going to do is we're just going to divide that vector by its norm. And this norm right here is just the square root of minus 2 squared plus 0 squared plus 0 squared plus 2 squared, just the sum of the entries squared, square rooted. And that's, in this case, square root of 8, or 2 square root of 2. So when we divide by that, what do we get? We will end up with minus 1 over square root of 2, 0, 0, 1 over square root of 2. So this 2 right here is going to cancel with both of those, and you're just left with square root of 2 in the denominator. So that's our second vector. All right, so far, so good. One thing that's pretty cool is you may notice, okay, the norm of this is 1. You can check that out. But also, this is orthogonal to the previous vector. So we're almost done. We got 2 of the 3 already done. But again, the third one's probably going to be the hard part because we have to project away even more things. So let's go ahead and get started. So we're going to start with our third vector. So the third vector here was 1, 1, 1, 6. And what we're going to do is we want to project away the previous ones. So we're going to project 1, 1, 1, 6 onto V1 and also project away onto V2. And I want to point out what we're really doing here. What we're really doing is we're projecting onto the hyperplane altogether of the previous vectors. So we're projecting away the projection onto the previous vectors and the previous subspace. And we can do that because these are already orthogonal. Those are orthogonal vectors. So we can the projection onto that subspace is the same thing as the projection onto the individual vectors. All right, so now we need to compute these two guys. So this one's just going to be the projection of 1, 1, 1, 6 onto 1 half, 1 half, 1 half, and 1 half. So we can write that as like this. And again, we're going to associate them like this. The norm of this bottom guy should be 1. You can check that too. And on top, we're going to get 9 halves. So we end up with 9 halves times 1 half, 1 half, 1 half, and 1 half, and divided by 1. So altogether, we end up with a vector that's just all 9/4. So that's part of what we're going to subtract away. And now we have to go to this other guy and do the same thing here. We're going to project 1, 1, 1, 6 onto the vector minus square root of 2 over 2, 0, 0, square root of 2 over 2. So we're just projecting onto this vector right here. All right, so we're going to take that vector. Let's write it as I did before. So it's minus 1 over square root of 2, 0, 0, 1 over square root of 2. We're going to do that again. Then we're going to do it 2 more times. And we're going to associate it just like we did before, like this. This norm here is still 1. Right, so this norm should always be 1. So we now know that the bottom, the denominator, should be 1 here. So now all it takes is to do the other dot product, which we're going to get 5 over square root of 2 times the vector minus 1 over square root of 2, 0, 0, 1 over square root of 2. And so altogether, we're going to get 5 over 2. Minus 5 over 2, 0, 0, 5 over 2. And we're going to subtract these vectors from 1, 1, 1, 6. Let's see what we get here. All right, so I'm mildly cheating. I'm using a computer, but when we're done with this, we will get 5/4 minus 5/4 minus 5/4 and 5/4. So this is our W. So that's the vector that we get when we project everything away. Now this vector itself is also not norm 1. It has an entry bigger than 1. So we have to divide to get our final V. We're going to go ahead and divide W by its norm. So this right here is just the square root of 5/4 squared plus minus 5/4 squared plus 5/4 squared. Plus 5/4 squared. So that ends up being 5/2. So we're going to divide everything by 5/2. So we're going to take our vector. This turns out to be a lot nicer than it would otherwise look. There are a lot of fractions. We're going to divide everything by 5/2. So this 5 here is just going to cancel with these 5s. And then dividing by 2 is the same thing as multiplying by 2. So we end up with just a vector of 1 and plus or minus 1/2. All right, so that's our final V vector. So there's our V3. So what's our answer altogether? Well, for the first vector, we got 1/2, 1/2, 1/2, 1/2. The next vector, we got minus square root of 2 over 2, 0, 0, square root of 2 over 2. I guess you can also write this as minus 1 over square root of 2, 0, 0, square root of 1 over square root of 2. And for the final vector, we got 1/2, minus 1/2, minus 1/2, and 1/2. And so we can see, okay, we didn't actually change the span of this vectors because we got these vectors by taking linear combinations of them. This seems very strange. All the vectors we get, we subtracted out linear combinations. How do we get v3. We subtracted out a combination of the other two vectors. So this is still the same span. We didn't change the span. All the linear combinations that you could get with the original ones are preserved. But on the flip side, these are all orthogonal. Those two are orthogonal. Their dot product is 0. The dot product there is 0. The dot product there is 0. And all of these have norm 1. So that's how you find an orthogonal basis and an example.